No, es líneas de altura.
Hi, everybody. So welcome to today's seminar, which will be given by Leo, which probably all of you know. And so I'm looking for a presentation.
Thank you all for coming. So this is a combination of the work I've done here at IFISC. And it's a very interdisciplinar project. So, well, the work wouldn't be done without the collaboration of several people. In particular, I have to thank Claudio, who, well, helped me to keep me on this smooth and straight track. That's this project. And, well, you already know also Ingo Fischer, Raul Vicente from here. Gordon people have been visited here several times. And Alessandro Villa, he's an expert on cortico-cortical circuit. And José Luis Cantero Mercedes Atensa and Maite Crespo Garcia are from Seville, and they work on, well, on DREAM, the DREAM Lab. And they are experts on the dynamics of hippocampus, and they do some experiments in humans, and they had some experiments also in mice that we had analyzed all the experiments with, well, good success. I'm going to show you next. So the point, well, the dynamical relay takes into account spatial temporal complexity. So I'd like to make first a brief overview. Well, single neuron, everyone knows, since elementary school. Well, the activity is, most of the activity comes through the dendrites, and it propagates and it's passed through the neighbors, through the terminal buttons on the axon. I'd like to call attention on the axon. It might be long, and it might be covered by myelin. So the myelin has, after a while, a white color. So that's why the white matter has this white structure. It is most composed of axons going from one region to a distant region. So this gray matter, it's most of the body neurons, of cell soma and cell parts. And then the white matter are from myelin. There are a lot of myelin connecting. It's a complex structure. For us, these long distance connections are important because they have some conduction delay. There is some conduction delay associated with it. And we are going to look at this. And it has a large complexity. And since 1669, it was already called the nature's finest masterpiece. Just a recent compilation of this macaque brain. well, if this it was done very early. So if you, well, they put these different regions in a circle. And if we look at all of those, it's going to be just a mess. Oh, this is pi, some of you already know. So, but one can put things together, the links together, and try to make the hierarchy structure more simple to understand, and that's the final outcome they got to. But then here they are, each connection is just, I mean, each region is connected just by one link. And in the reality, there are several connections, so it's a very complex structure.
Excuse me, what's the difference between the different pods? I mean, what did you do to extract this connectivity at the end?
No, this is the same thing as this, but they just put the links together. They have done anything. Just because this is just they just put all the areas and link. Well, they just straight. And when they can put together the links, and we can. I mean, that shapes the hierarchy structure better. Because otherwise, here we cannot see the structure.
I don't understand this mechanism of putting together the links. What?
No, just put. Oh, I don't know. Yeah, there are some over here. So they just put them together. So you don't see a lot of links. You see just, I don't know, most of them, a lot of them together as well. Just to see the hierarchy.
So the nodes or the nodes are staying on the same?
Sorry?
Are you moving the nodes also?
No, that's the magnetic brain. Most of the nodes are cortical structure, and there are some subcortical structure. The basal-ganglia and the thalamus.
The color code is the hierarchy.
Sorry?
The color code, what is the color code is the hierarchy?
No, that's just to illustrate. That makes. Well, but here you can see there are different, correspond to different regions. But yeah, it's small, you cannot see very well. But the reference is here. Because when it's interesting, you can go where that. Then I would like to call about the dynamics. Talk a bit about the dynamics. So every measure one can make on the brain, they are going to see oscillations. It occurs in different scales. So even subcellular structures already oscillate. At the neuronal level, one can see this. And also at the network level. Oh, but if one knows about synchronization, one can say, okay, but well, it's not a very big deal because synchronization occurs everywhere. Every interacting oscillatory elements tend to synchronize, so well, the effect of neurons to synchronize can be just a phenomenon. Well, they are connected, so they can synchronize. But else, I don't know. Otherwise, one can think that, well, just because for the same reason it tends to synchronize, it might have an interesting, well, play an interesting role for processing of the information. So somehow it may have learned how to deal with it. So that's what people think. So just recently it was written, synchronous activity of oscillating network is viewed as a critical middle ground linking single neuron activity to behavior. So it seems to be an important thing to have. Well, synchronous activity and oscillations. So if you want to look at the power spectrum of the activity, it is typically continuous. So they have a lot of different frequencies going on. And the frequencies have been associated with different states. So different functions, different frequencies. Well, this is the mice activity, one mice, awake mice.
When you say activity, what are you measuring?
I think this is EEG. They are making EEG, they are recording.
But EEG is a cellular.
No, it's
integrated.
Yeah, it's a large area. It's a mean field. I don't know. It's taking into account a large area. But yeah, in this case, these two corresponds to theta. theta rhythms, which is the highest for mice, and this is gamma, for instance. So there are different powers, or different frequencies going on here. And this is for a human during sleep, but I'm not going into detail on this. But just that, well, different frequencies have different, are associated with different states.
Can you say again where is gamma?
Gamma is here, 5. So it's 5 here.
It's not normally 40 hertz, gamma.
Yeah, gamma is here. Yeah, it's around, it's from 30 to 80 hertz.
Yeah, but in the growth it goes only until 6. So.
Yeah, no, maybe this is 4. Because it's here, yeah, it's 4. I'm sorry, 5 is fast. Yeah. Yeah, this is the logarithm of the frequency. And also, yeah, that's for human sleep. They're having a lot of discussion on this, but not.
But this is not the same plot as the one.
No, this is for human during sleep, and this is for mice during awake, just moving around. And also, well, when we look at oscillations, we see that disorders typically involve abnormal oscillations. And this is from low to high frequency, and low frequency tend to be more spread around, and high frequency more local. So most of the connections are local. So, high frequency has, low frequency has a large period. So in this period, it can recruit a larger number of region of neurons. So in lower frequency, the activity is typically spread, and in high frequency, this is gamma, it's more local. And also it can happen simultaneously at different regions, and we'd like to look at that. And, well, there is this interesting hypothesis. It's called communication through coherence. And it states that, well, when they are activated regions are going to oscillate. So when they, you imagine a small region oscillating, so the output's more effective because everyone is sending the activity together.
When you say oscillate, what do you exactly mean?
Yeah, they're synchronized. Well, in the region, most of the neurons, or several neurons, are active together. So if you look at the mean field and the local field potential, one would see oscillations. So this will affect the output and the input.
So oscillation is collective activation.
Yeah.
That's your definition of oscillation.
No, but the region that's going to be synchronous. So the activity is going to oscillate typically at a range of frequencies. It can change from one period to the other. It does not have to be in the same frequency.
So what is the activity? They are spiking, right?
Yeah.
So they spike together.
The neurons at the end, yeah, but not every neuron is going to spike together. If you look at it's different. If you look at the local field potential, which is an average over a large region, thousands of neurons, you're going to see smoothing or oscillations. And then in the neurons, some neurons might, in the peak, most neurons are going to spike. Not most, it depends. Can be just a few, but it's much more than in the down part of the oscillation. So yeah, that's a hypothesis. That's an interesting hypothesis that has been done a short time ago. And then I come back to this picture. This is the all together. So in the brain, the activity in a short time scale, the activity time is kind of fixed. So also there are some localized and they are in specific regions. They process specific type of information. Even it occurs in different areas. So at the end, this activity has to be integrated somehow. And that's the point. It has to occur dynamically without changing the network. So that's the point of the communication through coherence. So different regions are going to be oscillating, are going to be activated at different times, producing, well, cognitive behavior at the end. So, yeah, well, and then there is another, well, even stronger hypothesis that's binding my synchrony. That means that these regions are going to be linking together. Well, not only if they are coherent, oscillating, but they must be at zero leg. But that's not, well, we're not going to go into detail on that. Just to comment, well, for us it would be enough to say that the zero leg synchronization occurs between distant regions. And also they have some functions associated with this fact. So it typically appears in attention demanding tasks. And somehow it must be generated and controlled. So that leads us to the question we start with in the title. So how can zero-leg synchrony emerge in the presence of induction delays? And how can it be controlled? So the outline, well, I'm first going to tell about the mechanism I've been studying. And this mechanism allows us to think about the thalamus as the relay station. It's a natural way of thinking. It's a strong candidate. And also, we comment a bit on the hippocampus as playing this relay station, which is important for theta rhythms. So, the dynamical relay, well, this is the biggest paper, I don't know, for me. And, well, most of you probably know already. And it's very thorough. It comments about laser experiments, simulations, and neuronal simulations. So the idea is simple. So 3 lasers, for instance, they are connected with a large delay. They can synchronize at 0 lag, but the ones that are going to synchronize are the outer ones, 1 and 3. So the time trace is going to be like this, 1 and 3 identical pretty much. Meanwhile, 1 and 2 and 2 and 3 are going to be out of phase. Well, not perfect synchronized. And that can be seen also in the cross correlation. So the peak at 0 lag occurs for 1 and 3, and not for the other 2. And it was done also for Hodgkin-Huxley model. So neurons here are the burst mode. So the same thing happens, the same mechanism. 1 and 3 are synchronized at 0 lag, and the others are not. So that's a very robust mechanism. And in this synchronization, if 3 neurons are oscillating, and one connects them with a large delay, after some periods, in this case 100 milliseconds, these outer nodes are already synchronized at 0 lag. So this was known when I got here some years ago. And I've been working from later on the extension from these neurons to populations. In neuroscience, most of the things, or the important things, are thought to be taken care of by populations, not by single neurons. Some things are done by single neurons, but most of the things are done by populations. So we'd like to check whether this is robust enough to be seen in populations as well. So, well, we were working on these populations, so we made each population made of thousands, over 4,000 of integrated fire neurons, 80% of them are excitatory, 20% are inhibitory. It's like a recipe people know for cortical region. And inside the population, the delay in the synapse is very short, and between the populations, the delay is large. So that's our spatial relation. It's like it doesn't have any spatial configuration inside the region, but from one region to the other, it's supposed to be very distant. So you can have arbitrarily large delay associated with it. So when we extended from single nearest populations, we saw that it's robust. So each region is oscillating. So actually there is a balance. Each neuron receives a bit more excitatory input than inhibitory input. The external drive is just Poisson process, independent process in each neuron. So there is no structure in the activity, in the external driving. But then each region oscillates by itself. But if one starts with arbitrary initial configuration, we turn on the connections between populations at 100 milliseconds, and 200 milliseconds later, one can see that 1 and 3 are synchronized at 0 lag. So that can be seen on the cross correlation or on the raster plot. So at 0 lag are 1 and 3 synchronized. So that was interesting because it could have possible implications for neuroscience. So when we knew about that, we were wondering about the relay station, because here the three populations are different, but they are all random populations, so they are similar. They could be just 3 cortical areas, or this could be any other region, but we don't say anything about it. Just the simplest choice we've done for populations. But then we'd like to wonder a bit about the relay station. So yeah, as I was saying, the thalamus is the natural strong candidate. It occupies a central position. All, except for the olfactory stimulus, all the external driving come from the external sensory areas and come to the thalamus. So the thalamus passes through the cortex. So it must pass through the thalamus before reaching the cortex. And it's already known to be a relay station. So the thalamus has several different nuclei. They are roughly each one of those have a different corresponds to a different type of stimulus. But we'd like to make just a minimum thalamocortical model because this can be very complex. So we choose just arbitrarily one of those. So the external driving is coming to the thalamus, to the thalamocortical region. And also there is this ventral thalamus, which is inhibitory. So in the thalamus there is the excitatory part and the inhibitory part, and they are strongly connected to each other. And the inhibition typically is more local, and the excitation can spread, or can be long distance more often. So the thalamus is, it has this dorsal part and the ventral part. They are connected, and the thalamus receives the external driving and passes through to the cortex, to distant and different cortical areas. And there is also the feedback from the cortex to the thalamus. So this is an important loop, the thalamocortical loop. And for instance, people have claimed that rhythmic oscillatory properties of thalamocortical loops is involved in the genesis of cognition. Of course, this is very ambitious. We'd like to make just a minimum model, just a very simple just to understand serial synchrony in the cortical areas. So we just pick a single nucleo and 2 cortical areas to make this minimum cortical model. And to this end, well, we were working with Alessandro, who had been working with cortical system for, I don't know, 20 years or so. So this has a lot of parameters involved, and he was helping us a lot on setting the parameter regime we would like to work with. So in the model, the thalamic region is made of excitatory neurons, and the dorsal part is inhibitory neurons, and they are connected to each other strongly. And there is these cortical connections back and forth, and the cortical regions can be connected or not. And we use integrating fire neurons. So here excitatory neurons, inhibitory neurons, and here we use the same recipe, excitatory and inhibitory neurons. And we set everything, and the only parameter we are gonna move is the external driving over the thalamic region.
Sorry, what's R? What's the R region?
R is the ventral thalamus.
No.
The ventral thalamus. There is the dorsal thalamus, and it's covered by the ventral thalamus. And the ventral thalamus is mostly inhibitory. So those two are together, and then the inhibitory doesn't send long distance connections. So the long distance are excitatory. Yes.
Did I understand correctly that you're using the thalamus as a relay between C1 and C2, right?
Yeah.
But
you can think as the thalamus as those two.
Yeah, but still they themselves are coupled directly.
Yeah.
But could we then use the ansatz in the paper by Ingo and Claudia and so on? I mean, the relay scheme functions in that way that both nodes are coupled to the central node and not to each other. Otherwise, it would be a triangular coupling, wouldn't it?
Yeah. The point is that there is no symmetry here, because this breaks the symmetry. It's a different. Well, it's different from those two. If we put those 3 like these together, there would be just we can rotate, and there is no relay. There's no center element. But here the symmetry is breaking because this is a different structure. But then the motivation for this is because it happens. There are some cortical connections also.
This link between the 2 cortical areas will play against the synchronization. I suppose.
Yeah, if this is very strong, things can happen. But in this case, it turned out to be very robust for the model. But yeah, if this is very strong, things can.
Depends also on the delay that thing has, because it's different from the delay to the thalamic.
Yeah, we are using 8 milliseconds here and 5 milliseconds here. Yeah, well, it's a bit different also. Yeah, the delay also makes the symmetry different. But then we set the parameters, and we are looking at the external driving over this. And this external driving stands for the sensory stimulus that comes from the sensory regions. So the external driving over the other regions are just other brain areas that we are considering. So looking at the raster plot, this is the one cortical area and the other cortical area. The pink points stand for the spikes of excitatory neurons, and the blue dots for the spikes of inhibitory neurons. And this is the R region and the T region, the thalamic region. So in this configuration, the thalamus is receiving a bit more external driving than the others. So there is oscillations here, and also between the 2 cortical areas. Well, and then they are synchronized actually. It's really like, this is just some 50 neurons we randomly choosing. It's kind of hard to see.
Which kind of driving is a constant
Yeah,
input?
process
Is
into
a constant
everything in each neuron. Yeah.
and a constant rate.
Yeah. but independent from each other.
But I don't. What I don't remember in the original paper by Claudio and others, the driving was also on the same relay.
Yeah, every neuron was receiving.
Everyone or only the central?
No, everyone.
Okay. And now you are only driving the central.
No, everyone is receiving, but the center has a different rate. So that's the difference stands for the sensory stimulation. Because it must come from, pass through the thalamus to reach the cortex.
All the other areas receive nu zero frequency, while the T region can range from nu zero to higher or lower frequency.
Yeah, so here it's kind of hard to.
But they are independent inputs or the same input to all the.
Sorry?
Is the independent inputs?
Yeah,
Independent inputs to each one of the 4 areas.
Yeah. Every neuron is receiving external value, but independent for independent process and at the same rate. So, but then it can be kind of hard to look at what's going on here. But when look at the cross correlation, and to make this smooth picture, one needs to have like 100 trials, and then this smooth picture appears. This is the number of coincidences between C1 and C2. So the maximum number of coincidences occur at zero lag. So one can look at the frequency. So there are multiple frequencies here. One is faster and the other it's slower, but both of them is still on the beta and gamma range. So we suppose that the zero lag is important. So we call this the signal, and just the average, we call this the noise. So we'd like to know if this difference from the zero lag synchronization just to what to be expected by chance is important or not.
What do you mean noise is correlation 0.85?
Yeah, this is the average. If we look at the average of the curve, we are going to find this. So if you this is made, in order to make this graph, you take one neuron from one population and one for the other population, and you look at the number of coincidences they are going to have. So actually, you have to do this for many couple of neurons in many trials. So this is smooth picture just appeared after many, after a large average. So this would be just expected by chance, just by if there is no.
So you calculate the cross correlation between each pair of neurons at a given time.
Yeah.
At a given time lag, and then you average that, and then you get a plot in this figure.
Yeah, you have to make many pairs.
You calculate all the cross correlation between all the pairs.
Yeah, but
at a given time lag, at a given time difference, and then you get 1 point.
Yeah, but that's not cross correlation. That's the coincidence number. We look if there is coincidence or not. We are not looking at the continuous function. So we are looking just at the raster plot if there is spike or not.
And it's measured in hertz, you say? Coincidences? Is that S?
Yeah.
But shouldn't the zero lag peak then be at the frequency of the fire? If there was comparable magnitude? Coincidence.
No, the firing rate, the noise is given by the firing rate. You can just assume that they are independent. So if they are independent, you can calculate the noise, but not the signal. This is not a trivial function. It depends on the dynamics of the system.
Also, this in principle is not normalized. The fact that the maximum here is 1, it's just an arbitrary number.
This the number of coincidences.
So this one doesn't mean that all the neurons coincide.
No, it means that in average, there is one coincidence in a second.
But that depends on the number of neurons you have. If you have the double number of neurons, you have 2 coincidences per second.
No, but that's normalized by the number of
that's normalized by the number of pairs of neurons.
the proportion of coincidence.
So it's the proportion of coincidence per second.
Yeah. Well, the number of coincidences of different areas. Yeah. Yeah.
So the maximum would be n coincidence, or one coincidence.
Yeah,
What
there's
is the
no
maximum?
maximum. There's no maximum. There are coincidences.
There's no maximum.
It's not limited. I don't know. But then if we look at this ratio of the zero lag over the average expected as a function of the external driving over the thalamus, one see a local maximum. And actually, this curve here is when the feedback from the thalamus is taking up. So this feedback is important for the picture. And these triangles corresponds to when there is no connection between the cortical areas and the open balls, circles, correspond to when there is connection. So both of them turn out to have this local maximum. So that's interesting because it could be a way to control whether or not the zero lag synchronization is going to occur. So when the external driving is large, it can go to this region, promoting zero lag synchronization between the cortical areas, and otherwise it can inhibit. So just to illustrate, if the external driving is slow, well, there is not many coincidences and they are not synchronized. And then this is the maximum of the model. So there is going to be a large number of coincidences. So the cortical model promotes and controls zero lag cortical synchronization, but it's restricted to beta and gamma ranges. So we come back to the question of the relay station. And in particular, you pay attention that spark time precision is important for memory formation and for spatial information processing. And those two elements, these two are important for the hippocampus is very important for those two tasks. And the hippocampus has theta rhythms associated with it. So if you take the hippocampus isolated, it's going to oscillate in theta. So it generates these theta rhythms. And also another recent result that had no explanation, but they saw that the hippocampus and the prefrontal cortex phase lock. And they didn't know why, but they saw that it happens. So the dynamical relay could be interesting to explain this process. Well, it could be a possible explanation for this. They are looking at just two regions, but you can imagine there is another region, and well, that was what we did, and consider that the hippocampus is going to be in the relay station. So they were looking at, there was a phase lock between those two regions, the hippocampus and the prefrontal cortex. So then what we did was let's take into account the visual cortex as well. So if the dynamical relay occurs here, those two are going to be phase locked, and also those two are going to be synchronized at zero lag. So that's the model we made. Each region is receiving dependent external driving. And before doing the model, actually, this group, this lab from Seville, they were commenting. They had some experimental data, and they had not analyzed it in this sense. So this could be important to take a look and see whether this zero lag synchronization would occur, whether the hippocampus could be playing this relay, this row of relay station. So I went over there and I was looking at the data. It was pretty nice. It showed interesting results. So we were happy to be looking at to model this and see whether, we could see the dynamical relay here, but then we had a problem because we had not seen dynamical relay in theta band, and for theta it's a slow frequency, we were looking for something up to 10 Hertz. And if the neurons are in the regular spiking mode, we would not find theta oscillations. So what we did was to choose easy cavity neurons, so we could easily change the mode of the activity. So we put the hippocampus, most of the neurons in the hippocampus were in the burst mode. So this is just an example, 10 randomly chosen neurons for the hippocampus, the frontal cortex, and the visual cortex in our model. So those 8 first are excitatory and those 2 are inhibitory. So here they are just isolated regions. We are just looking at each region. So the hippocampus, most of the neurons were already having burst at a rate of 7 Hertz, or around 7 Hertz. As they've seen in the experiments, that the hippocampus was oscillated at theta, to generate theta, and then the frontal and the visual cortex do not show any oscillations here. This is the average of the population, it's just simple neurons randomly chosen. In the raster plot, one would see also the oscillations here. And here they are not connected, so that was seen that there's pretty much anything. This is a very small scale, and there's a lot of noise. In the hippocampus, we will see the oscillation smoothly. So
this was the coincidence between neurons in the same area, or what was the?
Yeah, this is in the same area. Different random chosen in the same area, from the same area. Yeah.
Coincidence between inside.
Yeah. We just need to have this picture to find this. So in the experiments they had, there was a mice, and it was either moving or not moving, but awake. And we'd like to model this. So in our model, we connected them like this, in this simple motif. So the hippocampus is clearly different from the others. The dynamics is very different. And when we connect, we see that the cortical area is synchronized at 0 lag, pretty much. And the hippocampus oscillates in a different mode, so sort of phase. So one would see between the hippocampus and the frontal area a phase locking in the experiments. So in order to move to model active and passive state, we just change the external driving. We consider that during the active state, the external drag will be larger. So we would like to compare this simulation with the experimental data. So in the experiments, they had like a large time trace, a local field potential measure. So it was like 1 minute of activity. And in the real data, there's a lot of things going on. It's not very simple. So instead of making an average of everything, we were chopping the big time trace in small regions. So instead of taking 1 minute, we would take 600 milliseconds and look at the cross correlation inside each of these windows. And for each of these cross correlation, we would pick just one point. That's the maximum of the cross correlation. And then we would consider for every single window, we take just the maximum of the cross correlation and see what was going on. And also before doing this, we would have to filter in the theta band. If we don't filter, we don't see such a large difference between the active and the passive state. So after filtering and looking at the density, where the maximum of the cross correlation at each window is, So we see that most of the maxims between the two cortical areas occur at zero lag for both passive and active state. And also there is this phase locking between the hippocampus and the cortical areas. And in our model, doing this, we would find similar structure for both the active and the passive state, just by changing the external driving over the populations.
Yeah. This difference in the delay time for the different cortical areas, where do they come from? Is it just that the coupling time is not really the same, or experimentally, or?
No, they might not be at the same distance, and the distance between the hippocampus and the areas might not be the same, so the time might not be the same, and they will not concern.
Yeah, we did this.
Just wondering why, because in the simulations
because we do the same, but we have simulation with different delays, and you can see the split of the two.
Yeah, we actually in the paper we used this, just changing the delay, and we find similar to this one. Well, but for a matter of time, I did it with this. But we could have. But yeah, this in the model could be explained, but just by changing the delay. And I don't know, with experiments, we don't know. Many things could be, I don't know, responsible for this. So yeah, we were happy because we could reproduce the experiments, and we saw dynamical relay in theta band also. Well, it was the first time we were looking at experiments for looking at dynamical relay in experiments. So to conclude, I'd like to say that the dynamical relay is very general and robust. So we've been finding many different systems and for different frequencies and for different delays. So in the thalamocortical model we did, the cortical synchronization could be controlled, and it also promotes this zero lag synchrony. In the hippocampus, we could find this in the experiments, in the theta rhythms for this dynamical relay. That's it. Thank you.
Did you leave? So, are there any questions?
Why is the thalamus not enough to make synchronization at all in all the bands? I mean, is it because of the parameters that, or what is different between thalamus and hippocampus?
Oh yeah, no, yeah. The thalamus. In the model, our model for the thalamus is much simpler than it is in reality. Because during sleep and stuff, it has slow rhythms. But in our model, the integrated fine neuron work was in the regular spiking mode. So we would never find bursts there. But yeah, the point is that to have bursts, in order to have this theta.
You mean that the spacing between the bursts is a large time, which is a low frequency?
Yeah, there's a slow current that makes this. This low frequency.
When you are separating things like, for instance, hippocampus and the other stuff, I understand. But for instance, when you are considering regions inside the hippocampus, how will you decide which are the regions that you want to analyze to compare the synchronization? Is it about functions that they develop, or there are some kind of physiological reasons, or how you separate the regions?
The thalamus, you mean?
Yeah, no, that's within the thalamus, or
no, because these two areas are very important. So actually, the thalamocortical area, that's the excitatory area, it's much more complex than what we have considered. We are supposing that that's just one nucleus, for instance. But then there are several others. But there is a close connection of the ventral part of the thalamus, which is inhibitory. So, this is well known. These two areas are work together to generate rhythms, and they are important, and people are wondering about this with thalamus. It's important for this relay to the cortex. Well, this is just a mini model for the thalamus.
Any other question? So maybe I have one. So it appears to me that you are taking so your model is quite complicated in the sense that you're including a lot of details, or you have hundreds of parameters as well. But so, and it also appears to me that you are actually changing a bit the topology in comparison with this idea of the two external elements which are synchronized through the middle one. So maybe it could be worth to study what happens when you connect these two external ones, and what happens as you ramp up the strength of that connection, and also when you change the delay of that. I could imagine that as you go changing the delay, you will have some resonances where you do find synchronization, and then there will be delays where you screw the synchronization and so on. Have you done something like that?
No, not a complete study like this. But yeah, we have seen some effect of it, but not everything, not this. But yeah, one could find interesting things as a function of this connection between the two distant components.
Well, at least in laser systems, if you move the relay element to one side, you will always get identical synchronization, but at the time lag, which is the difference between the two times. So now you have two branches with different delays, and the maximum of the correlation occurs at the difference between the two delays.
But
even if they are very, very separated, one can be very close to another.
If you join the external...
Then if you put the third connection, then the system is more complex, because the stability is much less, the relational stability is smaller.
Yeah.
You have to satisfy some symmetries. As soon as you break that symmetry, it can be unstable. So it can disappear. But if you don't have the third connection, you can have the middle element in the middle or moving out of the middle, and you still see identical synchronization with a certain slag, which is much smaller than the later.
Then I don't understand nothing. In the experimental plots and in the model, no, at least in the experimental plots, there were synchronization at zero lag between the two cortical areas, and then the two between hypothalamus and one cortical and hypothalamus and another cortical, there were not at zero lag.
Yeah,
and you said that the reason why there were at different times is because there were different delays.
I'm not saying that.
But
sorry. What I'm saying is that if you have this, and these delays are identical, the correlation is at zero.
Yeah, but if
between these two. If they are not identical, the correlation would be about here. And this distance is the difference between these two delays.
Yes, but in one of the plots, in the experiments...
Without this connection, be careful. Once you add the third connection, it can be different.
And here, in the upper plots, I see maximum correlation at zero lag. And you have just tell us that the explanation for the other correlations to be different is that they were different lag. But then the largest peak should be not at zero lag, but at the difference.
Well, that might be the influence of the third connection.
Yeah, but the experiments are, there is much more things going on. That's just a simple picture.
You're right. If we remove the third connection, we shouldn't get the synchronization at zero. If the delays are different.
And I don't know why, because of why they put in this connection, you go to zero. I don't understand.
Yes, it's a good question.
Yeah.
Can you say anything about the coupling strength between the visual and the frontal cortex in relation to the coupling strength to the hypothalamus?
The thalamus?
The H.
Oh, that's the hippocampus.
Hippocampus, sorry. The relation or the ratio of the coupling strength, can you say anything about that?
Yeah, well, what we've done is just well, it was a simple model. So we just fixed the parameters. So yeah, I have not explored yet. It's a large parameter space, so one can be exploring this for a long time. But I don't know for sure. Well, but the main point I think was what Emilio was wondering about. I think because the hippocampus, well, the hippocampus has a different dynamics. So you are comparing in the laser. Claudio was saying everyone was.
That's also true. We are comparing identical elements. These are completely different. So the idea would be more or less the same, but at the end.
Yeah, but it's strange that putting more different stuff, you get synchronization at zero lag. You expect that putting lots of different stuff, the zero lag will be the less likely.
But there is a symmetry between the cortical areas. They are similar. This region is different, but those two are similar.
Maybe because the delay between the hypothalamus and the other regions is the same. It's 20 milliseconds, and the other one is different. Maybe because.
Oh yeah, this could. I don't know. Let me go back again.
But this is for the hippocampus.
But yeah, the delay can be important. Yeah.
It is the only one that makes connection. From the hypothalamus.
Yeah, this is hippocampus.
The hypothalamus to the others is always the same delay.
Yeah.
In the model, not in
Not in the model either, because when we try to explain that the two small peaks do not overlap, we have to introduce an asymmetry in the two delays, 20 against 18 or 19.
And then you get zero lag synchronization between the.
No, zero lag remains, but the two side peaks split from each other, which is what is seen in the experiment, and not in the model.
Did you by any chance try simulating the case that the hippocampus does not really act as a relay but more as a driver, so that each frontal and visual cortex gets stimulus from two different but in essence more or less the same hippocampus as a driver?
Yeah, if that was the case, theta would not appear in the system. So the oscillations, the slow oscillations, would not appear because, well, the hippocampus here is generating this frequency.
So there was no zero lag synchronization then?
Could be, but not at this. Well, the oscillation would not be at theta. Because typically, I don't know, gamma or high beta.
But still, the dynamics could be synchronized.
Yeah, but we are trying to look at the hippocampus here.
So, any questions? If not, let's thank Leo.